This is a video about online convex optimization with unconstrained domains and losses. Online convex optimization is a game played in rounds. In each round, a learner first picks a point, WT, in some convex space, and then the learner is given a loss function, LT, which is convex, and suffers loss LT of WT. The objective is to minimize the regret, which is defined to be the total loss suffered minus the loss suffered by some arbitrary but fixed comparison point, U. Now this is an extremely general setting because the loss functions, LT, can in fact be chosen adversarially. As a result, algorithms that guarantee low regret in this very difficult setting can, and in fact are, applied successfully to much less general settings, such as, for example, stochastic optimization problems. Now we know from some lower bounds that the best regret we can possibly guarantee ourselves is of order b times L times square root of t, where b is the maximum norm of the comparison point u, and L is the maximum gradient that we see. These values b and L are parameters that our algorithm might need to know in order to guarantee this regret. Can we get away without knowing some of these parameters? Well, if we know L but don't know b, then there are in fact algorithms that can get this bound, at least up to log factors. Similarly, if we know b but don't know L, then again there are some algorithms that can get this regret bound. But what if we don't know anything at all? Well, that's the subject of this paper, and our first result is a lower bound, showing that it's in fact impossible to get this regret bound if you don't know b or L. You have to suffer an exponential penalty that depends on the rate at which the loss functions are increasing. How can you see this? Well, suppose the environment presents our learner with a sequence of loss functions whose gradients all point in the same direction. Then, in order to do well against a comparison point u that's perhaps exponentially far in that direction, our learner needs to pick WT points that move exponentially fast in that direction. However, if it does this, then it opens itself up to an attack in which the environment presents it with a new loss function whose gradient is really, really big and points in the opposite direction. This gradient is so big that it could wipe out all of the previous gradients and cause the learner to suffer a high regret with respect to the starting point, maybe the origin. This is of course a little bit distressing, but there is hope. If the loss functions don't grow too quickly without bound, then this exponential term actually reduces to a constant, and we can still perhaps do well. So, we provide an algorithm, which we call rescaled exp, that gets this regret bound without any knowledge ahead of time of b or L. As a result, rescaled x is naturally hyperparameter free. It requires zero tuning whatsoever. Further, we show that in practice, rescaled x performs empirically just as well as algorithms that do require hyperparameter tuning, suggesting that this exponential term really doesn't come back to bite you in the real world. So I'm about out of cards. If you want to know how rescaled x works, I encourage you to please read my paper. And that's it. Thank you.